All right, very good afternoon, everyone. So now it's turn for Group 1. Their topic is Basic Theorem of Boolean Algebra, and the participants are Anani, Ayush, Anveshi, Ayush, Gupta, and Tavishi. So now let me just give you the share screen option. It has been activated. Okay, so I will request the first participant, that is Ayush Gupta. You can start your sharing at your end. I think Ayush, test your mic once, say something so that
हेलो सर।
हाँ it's audible. Your camera is off बेटा, क्या possible है कैमरा ऑन करने का? नहीं है तो no issue in that one.
सर वो देख रहा हूँ मैं।
हाँ
सर आई थिंक इट इज नॉट गिविंग सर
no issue,
विथ
no
मोबाइल।
issue, no issue, no issue. You can begin your presentation. Yes.
सर
Yeah.
नाउ इट इज ओके।
हाँ yeah visible.
सो this good morning respected sir and all my dear friends. My name is Ayush Gupta and I am here to present a small presentation based upon CS subject, and our topic is the basic theorem of Boolean algebra. So enjoy yourself and see the presentation. So we start with the topic itself, that is Boolean algebra. So in mathematics and mathematical logic, Boolean algebra is the branch of algebra in which the values of the variables are the truth values, that is true and false, usually denoted by the 1 and 0 respectively. Here we can see that the creator of Boolean algebra was an English mathematician whose name was George Boole. He helped in establishing the modern symbolic logic, and whose algebra of logic, now called Boolean algebra, is as basic design of digital computer circuit. Here you can see the image of George Boole, who was the creator of Boolean algebra. His birth date is 2nd November 1815, and he was passed away in 18 December 1864. Origin of Boolean algebra. Boolean algebra traces its origins to an 1854 book by mathematician George Boole. In that book, he distinguished the factor of Boolean algebra is that it deals only with the study of binary variables. Most commonly, Boolean variables are presented with the possible values of 1, which is true, or 0, which is false. What is the Boolean algebra used for? So my dear friends, Boolean algebra is used to analyze and simplify the digital logic circuit. It uses only the binary numbers, which we all know that it is 1 and 0 only. There is also another name of Boolean algebra, and hence it is also commonly known as binary algebra. Thank you, friends. This is all from my side, and for the further presentation, I would like to call Ananya Pandey.
Thank you Ayush. Anani, you can start it please.
Sir, Tavishi will screen share.
You have to stop the screen sharing Ayush, so that others can do it. Yeah, thank you. uh, Tavishi, please begin the sharing. Yeah.
Good morning to one and all present here. I am Ananya Pandey of class 11 science, and I am here to present my topic, basic operations of Boolean algebra. So as we know, Boolean operators are the simple words which are and or not, and they are used conjunctions to combine or exclude the keywords in a search, resulting in the forward and productive results. So there are the three types of Boolean operations I'm going to explain, which are logical OR operation, logical AND operation, and logical NOT operation. First is logical OR operation. So consider two variables a and b. Since we know that it is Boolean algebra and it is represented by only two variables, which is one, either 1 or 0. So logical OR operation is denoted by a plus b, but it is always pronounced as a or b. So consider case 1 where a or b is equal to 0 or 0 is which gives us 0. In case 2, a or b who have the values 0 or 1 is 1. In case 3, a or b gives the with the values 1 or 0 gives its product as 0. In case 4, when there's a or b and their values are 1 and 1 or 1, their product is 1. Next slide. In logical AND operation, we consider two variables which are a and b. In logical AND operation, it is denoted by dot between the two variables, and here it is written a dot b. In the case 1, a and b's their values are 0 and 0, which gives us our outcome 0. In case 2, there are two variables. In case 2 also, there are two variables a and b. Their values are 0 and 1, and their outcome is 0. Similar in case 3, a and b 1 and 1 and 0, and their outcome is 0. In case 4, a and b 1 and 1, and their outcome is 1. And we always show and explain these things by, in Boolean algebra by a truth table. A truth table is a table which is used to represent all the possible all the possible inputs of the variables and their corresponding outcomes. It is always used to represent uh, expressions and Boolean numericals also and Boolean laws. So the third one is logical not operation. Logical not operation is always represented by only one variable. So here we take for logical not operation, variable is used a. It is used with either an apostrophe or an overhead bar. So here I am using an apostrophe. So consider case 1 where a's value is 0. So corresponding to it, a, a and apostrophe, its value is 1. In case 2 where a's value is 1, corresponding to which a's value is 0. So that's it for my presentation. Next, I would like to call Anveshi Bajpai for further explanation.
Okay, thank you, Anani. Anveshi, you can start.
A very fine morning to one and all present over here. As my teammates already told you about our presentation, so I'm going to explain about laws of Boolean algebra. So the first law I'm going to start is the identity law. This law states that when any variable is added to 0, the sum is always equal to the variable. For instance, let's take the variable as a. When a or z or 0, the result is a. Or when any variable is multiplied to 1, the product is always equal to the variable. A and operator then 1, it's a. So our next law is the idempotent law. This law states that when any input is added or multiplied with itself, the result is always equal to that input. Like a or a gives a when the variable is added to itself, and the next one is a uh, into a, it gives a when the variable is multiplied to itself. So now the third law is the dominance law, also known as the annulment law. This law states that when a term is multiplied to 0, the product is equal to 0, or when a term is added to 1, the sum is always equal to 1. We can see the truth table and the expressions already in the slideshow. So I'll move further. The next law is the double negation law. A term that is inverted twice is equal to the original term. A bar equals A. A double complement of a variable is always equal to the variable. So now we move for the last law, that is the complement law. When a term is multiplied with its complement, the product is equal to 0, or when a term is added to its complement, the sum is equal to 1. A dot A bar gives 0 and A plus A bar gives 1. So that was all for my presentation. For further explanation, we have Ayush Tiwari.
Thank you, Anveshi. Ayush,
Yes, sir.
yes, you can start.
Good afternoon to all of you, respected sir and all my dear friends. Today I am here to give a presentation about my topics, laws of Boolean algebra. Such slide is not coming.
Associative law, I can see it, beta. It's there.
Oh,
May-
yes,
huh.
yes. So first of all, laws of Boolean algebra. So basically there are three laws: associative laws, distributive law, and absorption law. So let's start with an associative law. Associative laws for the Boolean algebra. This law is for several variables where the OR operation of the variables results is the same through the grouping of the variables. This law is quite the same in the case of AND operators. So at the down you can see in bracket a plus b plus c is equal to a plus in bracket b plus c. So actually it's about the fundamental operations. So they are the variables and the plus is the fundamental operations. So Boolean algebra consists of fundamental operations of addition and multiplication. So upside one is of addition and downward side is of multiplication. Next line, truth table. So associative law can be proved with two methods. One which was given in the earlier slides and the second is by the truth table. So truth table for the associative properties. So actually I have taken the three variables a, b and c, but you can see the values, and after that I have added the variables b plus c and a plus b, and after that the results of a plus in bracket b plus c should be equal to in bracket a plus b plus c. If they are equal, thus associative properties of the Boolean algebra is been verified. So you can see all the results have been equal, thus it's been verified. So here comes the next law, the distributive law. The distributive laws for Boolean algebra. This law is composed of two operators, and or. You can see plus and multiplication too. Let us show one use of this laws to prove the expression. Here it's given proof. The proof is too long, you can see. The fundamental operations are two used here with the variables consisting of a, b and c. And the first one is given in the upward side and the second one is in the downward side. And the proof is given downward. So the proof is too much long, so not to waste time, let's go to another slide. So distributive law can also be proved with the help of truth table. So the truth table of the distributive laws of the truth table. So here also the same as the associative law. I have taken the three variables a, b and c as I have took on the associative law. After that I have added the variables b plus c, and I have took the final, what would be a final amount, means a in bracket b plus c should be equal to ab plus ac, and after that the result, if the all the results would be same, thus the distributive law is also been verified. So you can just check it. So here comes the absorption law. The absorption law, I think so in my concept it's too much easy. The absorption law states that x or in bracket x and y is x and x or y is x. The theorems of Boolean algebra can be proved using Huntington postulates. If you want to learn the absorption law in too much depth, you can just go and search in Google of the Huntington postulates. It's given is too much brief. Each postulates and theorems of Boolean algebra has two parts. One is dual of another. If one part is proved, the another one can be proved using duality principle. as it's given in the De Morgan's theorems. Next slide. So this can also be proved via the truth tables as we have done of the associative property and the distributive one. So here also the two variables x and y, and after that we have took the additions of the variables x and y. After that the results x in bracket x plus y. So my parts ends here. So
Thank you,
thanks for
Ayush.
watching.
Thank you, Ayush.
And I would now request the Vishi for further continuation.
Thank you very much, Ayush. So now comes the very interesting part. So to many people, mathematics is a collection of theorems. For me, mathematics is a collection of examples. A theorem is a statement about a collection of examples, and the purpose of proving theorem is to classify and explain the examples. Let us now see the most interesting collection of example. I mean theorem, that is the De Morgan theorem. So basically, there are two theorems introduced by De Morgan. This is the first one. So the De Morgan's first theorem. The complement of a product of variables is equal to the sum of the complemented variables. In this slide, you can see that I have used logic gates also to prove it. Beside this, as Ananya told, everything in Boolean algebra is explained by truth table. So we have two inputs here, that is variable A and B. And using the De Morgan's theorem, we have got the outputs. So if the value of A is 0 and B is also 0, using the theorem, we get both the right hand value and the left hand value equal. This is the second theorem of De Morgan. The complement of a sum of variable is equal to the product of the complemented variable. As you can see here also I have used two variables, and by seeing the truth table you can easily see that if the right hand value and the left hand value is equal, so the theorem is proved. Before moving further, it is very important for you to remember the other laws and postulate that were already being explained by my teammates, because in the next slide we are going to prove it. So here comes the tricky part. This is the proof. So I will be telling you some tips for proving also. So first let us see the proof. So I'm taking here a variable which is p, which is equal to a plus b. Also, the yellow highlighted lines are the theorems, which are theorems and laws which are already told by my teammates. So let p is equal to a plus b. So the first in the first line we can see that I have used a complement law, and by substituting in third line we get the two statements. But by using the De Morgan's law, we need to prove that a plus b in the whole bracket plus a naught into b naught is equal to 1, and a plus b dot a naught dot b naught is equal to 0. So we need to prove one of the statements. As you can see, now proving a plus b plus a naught into b naught is equal to 1. In the next line, we are using associative law, which is very well told by my teammate Ayush. And using the property of 1 and 0, we can easily prove the De Morgan's law. And similarly, the proof is it gets very easy. Now, tips for proving. So all face very big difficulty in proving the De Morgan's law. But here's a tip for you. Uh, you need to learn any one of the theorems of De Morgan and use the principle of duality, that is changing uh, changing the operations. For example, a plus b dot c. So here the and or operator you can replace after proving any one of the theorems, and you will get the theorem proved. So this is the flexi that we prepared.
Thank you very much,
Thank you
Tavishi.
everyone for watching.
Okay, so this was the last member, Tavishi. Okay, a good presentation. I'll stop the recording for a while. Just a moment.